Back by popular demand is Toby to tell us about higher Segal space.
Thank you very much for the introduction. So what I'll be talking about today is based on various works. So one is joint work with Mikhail Kopranov in progress, and there's some independent work of Thomas Pogundke, which I will refer to. And then finally, in the end, I'll hope to get to some joint work as well in progress with Gustavo Jasso. So Gustavo and Thomas are in the audience. So again, you can ask them more details if you like. So, so yesterday we've seen some rudiments of this notion of a two-Segal space, and what I'd like to begin the talk today with is to actually revisit with some more detail one of the applications I was mentioning yesterday, and that application was of the following form, namely it was about the construction of surface invariance from such a two-Segal space. So more generally, I'd like to now just begin with a two-Segal object. So this would be a simplicial object which takes values in some infinity category C. So this will always be, for this whole talk, an infinity category which is supposed to have finite limits, let's say. And then what we have seen is that the lowest three-Segal condition, it sort of had this geometric interpretation in terms of the following picture by looking at the three-simplex. And then these two two-dimensional membranes which lie in the boundary of this three-simplex, which are obtained by looking at the two different possible ways of triangulating it. So if I triangulate it like this, then I get the two faces, which in the current projection lie in the back of the simplex. And if I do it the other way around, I see the two faces that lie in the front. And we saw that that was the lowest condition which that two-Segal object needed to satisfy. It was that if you look at the map from the three simplices, then this is equivalent in two different ways to this fiber product of two copies of x2 corresponding to the two triangles and connected along the common edge. So these two maps are equivalences. And now what this picture suggests is that I may actually interpret this sequence of equivalences, for example, if I invert one of these arrows, as a way to flip from one triangulation of the square to the other triangulation of the square. And so this is precisely the idea which we will now try to exploit to define surface invariance. And so this goes as follows. So what I would like to do is, I would actually like to start with some surface, say compact surface, which looks like this. So surface S. And then the surface is supposed to be punctured at a bunch of marked points. So with punctures, let's call there's a finite subset of punctures in the surface. So let's say the surface something of genus 2, and then there's a bunch of punctures which I draw as these vertices. And then somehow interpreting this picture here as a Pachner move of type 2-2, which allows me to flip locally from this triangulation to this triangulation. The idea is now that I want to play this game on the surface itself. So I just look at these points and I start drawing some triangulation. So say like this, and so on. And now what I'd like to define an invariant associated to the surface whose definition will be based on this chosen triangulation. So let's call this triangulation maybe T, just as we did before, denote the triangulations of these polygons which we're considering. But now more generally, you have a triangulation of this compact surface. And what we're trying to do is we're trying to evaluate this simplicial object which we have here in precisely the same way by this formula which takes a limit over all the simplices that appear in this triangulation. So this would be the following attempt. I somehow try to say that I would like to define an invariant of the surface, which is defined by a formula somehow of the following kind, if an xt, and I'd like to define this as a limit over all the simplices that actually that actually appear in this triangulation, and then xn. So this is what I'd like to define, and then I would hope that this is actually independent of the chosen triangulation, because I can apply this local move here. But now there's a problem, because this formula actually doesn't make sense. Because if I look at these vertices here, and I look at this triangle here, then its vertices do not come equipped with a linear order. So I actually cannot make sense of this diagram, because x expects as an input some linearly ordered set. So one way would be to just kind of brutally linearly order all these vertices and then make something with it, but then I would get an invariant which depends on this linear order, and I wouldn't like that. So what we do instead is the following. We actually observe that if the surface comes equipped with some additional datum, let's say some additional structure like an orientation, then actually, if I look at each of these triangles, then using this orientation, these vertices actually come equipped with a canonically chosen cyclic order, corresponds to this triangulation. And then the idea is that what I should try to do is to slightly upgrade this object so that it doesn't expect as an input a linearly ordered set, but it's actually sufficient to provide a cyclically ordered set. So what this means in technical terms, in terms of the simplex category, is that, I have to erase here a little bit, is that there's a natural category in which the simplex category sits inside, which is the so-called cyclic category of Olancon. Okay, so roughly speaking, while here the objects are just the standard linearly ordered finite non-empty linearly ordered sets with maps preserving the linear order, here the objects I should think of as cyclically ordered sets and the maps preserving the cyclic order. It's not quite that. One has to be a little careful how to really set this up, but this is maybe good enough for now. And so now it's sort of a question whether this object x here has a sufficient amount of symmetry to extend to such a cyclic object here. So let's assume we have that. So if I can find this lift of x to the cyclic category, then it actually turns out that I can just make sense of this formula, because now the expected input is a cyclically ordered set, but I have that because the orientation provides the cyclic order. So now this formula makes sense, and then what this observation here tells me, that I have these equivalences, it tells me that I can actually modify this triangulation locally without changing the result of this limit. I can, for example, swap this diagonal to the next diagonal, and so on. And so the first result I need is that actually any two triangulations of the surface that only involve the vertices that I have prescribed can be connected by a chain of such local moves. So that's actually a rather easy result to establish. And so what this means is that whenever I write down two different triangulations and I write down this limit, then there's a possible path of flips which connects one of these triangulations to another, and therefore I get an equivalence of one of the results with the other results. Okay. But that's kind of possibly unsatisfying, because there may be another way to start flipping triangles in a different, flipping squares in a different way, and I get a different way to exhibit an equivalence between the two answers. So I'd like these to be identified, and then again, there will be a certain choice of identification, so there may be two possible ways to identify them. I'd like those also to be identified. In other words, I'd like there to be an essentially unique way to identify xt with any other xt prime corresponding to another triangulation. Okay. So, and what the statement is, that precisely the higher Segal conditions that are captured in this two Segal object, they give me precisely the data which allow me to deduce this statement. So let me explain, maybe in a slightly more technical language, how to do this, because it's actually rather easy. Namely, what I do is the following. Instead of just looking at triangulations of the surface, I actually look at polygonal subdivisions. So I also allow squares and pentagons and so forth. And so let's denote, and so those collections of gadgets actually form a poset, which is ordered by refinement. So let's look at this poset. So I have a poset, let's say P, which depends on the surface and the punctures. Okay, so, and this is, let's say, the poset of polygonal subdivisions. And so what we say is that this construction here, it of course works more generally. If I look at this polygonal subdivision, I just look at the limit of all simplices that lie inside it, and so that actually then provides a map into the category C, let's say, which takes any such a polygonal subdivision, let's call this maybe sigma, such a subdivision, to precisely this formula here, x of sigma. Okay. Now, what these two Segal conditions make sure is that whenever I choose a refinement, then the corresponding map, which is the map from x sigma, let's say, to x sigma prime, which is a refinement, is actually an equivalence. That's just an easy consequence of all these higher two Segal conditions. So in other words, what I'm looking at is a diagram in this infinity category C that is parametrized by this poset, but it sends all the inclusions in this poset to equivalences here. In other words, it factors through the localization along all the edges in this category. So this I can think of as the singular Segal complex, which is a singular simplicial set of the geometric realization of this poset. So this is what I obtain. So this is due to the two Segal conditions. That this exists. And now it's a beautiful classical result, which is actually quite non-trivial. So it was, for example, originally proved by Harrer using methods in complex geometry. So he related this to the contractibility of Teichmüller space. And the statement is that this topological space, which I obtained by realizing this poset, is actually contractible. So this guy here is actually contractible. Which somehow says that not just is it true that there is an essentially unique way to do this flip-flop, to go from one triangulation to another, but any two ways of doing these flip-flops can be related by some higher dimensional cells, and so forth. Okay. So what it effectively says in our context is that I have a map from this contractible space into C, which means that I have an essentially unique object in this category C, and this is precisely the desired invariant which I wanted to construct. So it doesn't depend on any choices up to, well, it only depends on a contractible space of choices. So I should say that this technique of producing invariants of surface, which arises in the subject of topological field theories, it's actually very close to the original ways that physicists would use to construct these things. So for example, maybe the most elementary kind of this construction would start with a symmetric Frobenius algebra. It would choose a basis of this Frobenius algebras, which is labeled by, let's say, which has some labels, and then I do the following game. I compute what is called a state sum. I choose a labeling of all these edges that appear in the triangulation by basis elements. Then I look at the structure constants of the composition law in this Frobenius algebra with respect to this chosen labels. That gives me some number for each triangle. Then I take the product over all these numbers for each triangle, and I take a gigantic sum which sums over all possible choices of edge labels. And then the statement, which is more or less precisely of exactly this form, is that this doesn't depend on any of the choices due to two things: the associativity of this composition law captured by this algebra, and number two, a certain cyclic symmetry in the structure constants of this Frobenius algebra. So what we're defining here is simply a categorified version where we just kind of explicitly capture this cyclic symmetry in the structure constants on this level of the cyclic category. So it's nothing really fancy, but it's rather just kind of the most explicit, if you want, ad hoc way to construct surface invariants of TFT style based on very traditional ideas in physics with a slight upgrade by using this infinity categorical language. Okay? So in other words, what I somehow learned from this is that we said that one way to think of such a two-Segal space is to capture this multivalued composition law. What this perspective tells me is that I can think of it alternatively as some kind of a gadget that that captures a coherent system of two Pachner moves. Okay, so if I can think of, if I want, a two-Segal space. It's kind of the same thing as just a coherent system of two Pachner moves. So, which I can therefore then, whenever this two-Segal space comes equipped with a sufficient amount of additional symmetry used to provide surface invariance. So coherent system of two Pachner moves. Okay, so now one neat aspect of this construction is actually that it doesn't just work for the cyclic category, but actually, for example, if I didn't like to choose an orientation on this surface, it's an unoriented surface, then I have to pay a price, because then I have to provide more symmetry on this object. I would then have to specify what is called a dihedral object. If I put some more structure on the surface, such as, for example, a framing, then I have to provide less symmetry on this object, which would be given by a lift to what is called the paracyclic category. And if I do something in between the paracyclic and the cyclic category, then I would have to provide things like n-spin structures. So there's a whole dictionary, as we kind of know from more fancier statements of the cobordism hypothesis, which relates these structured two-Segal objects to surface invariance, where the surfaces come equipped with a certain reduction of the structure group. So what I was telling you then is that there is actually a very interesting example of such a TFT, which one can construct in this language, which was just previously not constructed. So that's why this, even though it's an ad hoc method if you want, it can be really used to explicitly construct new examples of TFT. One of the examples was, for example, given by the S-dot construction, where C was simply the infinity category of stable infinity categories, for example. Then I look at the S-dot construction of any stable infinity category. That's going to be an object of this kind. It always has a canonical paracyclic structure, so therefore what I can get from it is I can get invariants of framed surfaces, and those have a very interesting interpretation as sort of degenerate combinatorial versions of interesting categories that arise in symplectic topology, which are called Fukaya categories. And so now I guess if you look at it this way, there's an obvious question, because, for example, these Fukaya categories make sense in higher dimensions, and so they're actually very difficult to compute. So, and this technique really provides like a combinatorial approach to effectively compute these categories. So it's very tempting to have a version of this kind of a framework in higher dimensions, which then in the end would hopefully provide me with combinatorial constructions, for example, of these Fukaya categories arising via some sorts of TFT. So this is the goal of a general sort of long-term program, and what I'd like to explain today is kind of the first sketches, which hopefully convince you that this is not completely hopeless. So in other words, I would like to, for example, have a version of 3 Pachner moves, 4 Pachner moves on some even-dimensional manifolds. I expect them actually to be even-dimensional because they're supposed to come from symplectic geometry, and that will actually happen, and so this is what I'm going to explain. So in other words, we need higher dimensional analogs of these Segal conditions that are designed to capture some notions of coherent systems of these Pachner moves. Okay, and so this is what I'd like to start explaining now. Any questions so far? Okay, so and the combinatorics which we will use to address this question is the combinatorics of a very beautiful class of polytopes, which are called cyclic polytopes. And so those I'd like to define next. So let D, let's say, bigger or equal to 1, and consider the following embedding of the real line into R to the D, which is just in coordinates given by mapping T to T squared, T cubed, all the way to TD. So this is the starting point. Then further consider some finite subset S of the real numbers, finite subset, and define so what will we define? We define the cyclic polytope on the collection of these points S in dimension D to simply be the convex hull of the image of these points under this map nu, of nu of S. And so this is going to be some subset, therefore, of R to the D. Okay, and so this is called the cyclic polytope. So the d-dimensional cyclic polytope on this set S. Okay. Let's look at just a few examples to understand how these polytopes look like, and to also introduce you to the way we'd like to think about these polytopes when relating it to these to these higher notions of Segal spaces. So examples, let's say, the following. So I'd like to set S to just be, I think I wanted to do like, so I'm going to write this just for the usual ordinal, considered as a subset of the real numbers. And I'd like to put D, well, so D will now D will now actually increase. So the first thing to start with maybe is that if I actually look at, so what is the idea of using this map? The idea is just to somehow take a bunch of points given by this finite subset here and to put them into d-dimensional space in general position, okay? And then I take the convex hull. So what's actually true is that the combinatorics of this polytope, so the combinatorial lattice of triangulations in it actually doesn't depend on the choice of the subset S, so it's a purely combinatorial gadget. And the idea is really just that I'm trying to understand a certain number of points in general position in RD and how their convex hull looks like. So let's look. For example, if I start as follows, if I look at 5 points in general position in a 4-dimensional space, okay, then what I get is actually just the 4 simplex. Okay. So this is one easy case. And then sort of nothing happens beyond that dimension. If I send these 5 points in here, I just get a copy of the 4 simplex just embedded into some higher dimensional space, so nothing starts happening from here. And I can start in some lower dimensions. So for example, I can start with embedding these guys into 1-dimensional space. Okay, so then I actually just get the real line. And I get the points 0, 1, 2, 3, 4. So in this dimension, I simply get an interval. So that's also kind of boring, seemingly. And then the interesting stuff kind of happens in between these extreme cases. So let's see what happens, for example, if I put this in dimension 2. Well, in dimension 2, I now have to draw some 2-dimensional picture. So it looks like this. I look at the graph of this embedding here. It's going to be some parabola, so I draw it somehow like this. And then what I have to do is I have to embed these points 0, 1, 2, 3, and 4. Okay, so now the genericity assumption in this dimension is now simply that no 3 of these points lie on a line. So that's in that sense they're generic. And so now I'm looking at the convex hull, and I see what I get is actually a convex polygon. Looks precisely like this. And then there's one remaining case, which happens in between here. I look at 4 points in 3-dimensional space. And so now, try to draw this somewhere here. So basically, I'm just drawing the same picture as I did down here. But now imagine that this curve comes twisting towards me, let's say. So I draw this z coordinate here, x, y, and z. And so now I again look at these points, 0, 1, 2, 3, and 4. But now this point 4 here kind of lies very far towards us, and if I take the convex hull, it's going to be some three-dimensional shape, which actually, if you work out precisely what happens, it has these triangles that I'm drawing in a solid way that lie on the top of this polytope, the way we look at it with respect to the z-coordinate, and then there's other triangles which lie behind. So they kind of look like this. Okay. And so now there's a few interesting things to say about these polytopes. For example, these polytopes, they actually don't just come separately, as is maybe already kind of clear from drawing the picture like this, but there actually exist natural projection maps that are simply given by forgetting the last coordinate, and then obviously by this formula I just project onto the next guy. So there's going to be a projection map down to here, which forgets the last coordinate, projection map here, and a projection map here. And so what I can do now is I can play interesting games relating these polytopes to one another, and that's the reason why these polytopes and their triangulations are so well understood, because they're related to one another. For example, one thing I can do is the following. I can start with this polytope here, which is just an interval, and then I can look at the polytope in the next dimension, and I can kind of look up. Okay? So because these polytopes, due to the genericity assumption, are simplicial polytopes, their boundary is actually simplicial. So what I see, if I look up from one of these polytopes in the next dimension higher, I actually see a triangulation of the polytope I'm standing at. So for example, if I look at this polytope from the bottom, I see precisely these edges appearing here, and that's a triangulation of this interval. Okay, so this is what we will call the lower triangulation. So there are always two triangulations. There's one, in this case, which is given by the edges 0, 1, 1, 2, 2, 3, and 3, 4. And then there's the upper triangulation as well of this polytope, which is in this case just given by looking at the next polytope in the next dimension, but from the top. Okay, so therefore it only has one edge, which is 0, 4. It's also an allowed triangulation. Now I can do the same thing in this dimension as well. I can look at this polytope. I can look up. I can look at the next dimension from sort of a very small, a very negative z-coordinate, and then I will see a certain triangulation of this polytope. And so this triangulation, which I will see in the bottom, will then be 0, 1, 2, 0, 0, 1, 2, 0, 2, 3, and 0, 3, 4. Okay? And then again, there's going to be an upper one, which I get by looking at this guy from the top, and so I see another triangulation, and this triangulation will then be 0, 1, 4, comma 1, 2, 4, and 2, 3, 4. So this is one game I can play, therefore. I can also do this, of course, in the next dimension. I cannot really see this, but of course, formally it still works. So, and I will get the lower triangulation, which would be 1, 2, 3, 4, 1, 2, 4, 0, 0, 1, 3, 4, and then I get 0, 1, 2, 3. So this is a certain a three-dimensional triangulation of this polytope, which I get from sort of in the next fourth dimension, looking at the next guy from the bottom, or I can look at it from the top, and I will get another triangulation, and that will be 0, 2, 3, 4, and 0, 1, 2, 4. I'm not able to see in 4 dimensions, but there's a certain reason why I'm able to write this down, which is because there's a very simple combinatorics that allows me to actually write down these triangulations. Okay. So there's other things I can play with these polytopes. For example, vice versa. If I'm given any triangulation of one polytope in low dimension, then I can actually lift it simplex by simplex to get a section of this projection maps. And there's very interesting games I can play, for example, relating the height of these sections and trying to flip from one of these sections to the next section, performing certain local moves to these triangulations. So this collection of polytopes actually already has an interpretation in terms of higher category theory. Namely, I can actually, inside of these polytopes, really sort of visually see, in a geometric way, Street's notion of the Oriental. So that's the free omega category generated by the n simplex. So I won't have time to get there, but this is already one relation to higher category theory between which relates this family of polytopes to the subject of this conference. I'm happy to explain some more about this. This is some beautiful story. So. Okay, and so now, this motivates, or this sets us up to provide a definition of what is supposed to be a d-dimensional Segal space. Namely, what we're going to do now is we're going to formulate a descent condition, which is based precisely on these upper and lower triangulations that canonically exist for any of these cyclic polytopes. So this is the following definition. So let's see, again, the infinity category, and d bigger or equal to 1. Then, so then we define so a simplicial object x dot from delta up into C is called a lower d Segal object if for every n, so I need now n, so I need bigger equal d, I guess. The map from the n simplex into precisely the limit given by all the simplices, let's say delta k, that appear inside the lower triangulation, which I construct precisely in the way which I've explained above, of the cyclic polytope on these vertices n of dimension d. I take xk is a weak equivalence and similarly I define an upper Segal, upper d Segal by the same condition using the upper triangulation of the given polytope. C and D. Okay, so maybe let me just give you one more example that you can actually draw. So how to get these triangulations. I think I won't be able to explain how to describe these triangulations in a combinatorial way, but there's a simple combinatorial beautiful formula due to Gale. This is coming from this studying the combinatorics of triangulations of these cyclic polytopes, which basically is a criterion which allows me to just write down a subset of the ordinal n and decide on counting a certain combinatorial behavior of the gaps of this subset, which allows me to decide whether the simplex that is parametrized by the subset actually belongs to the upper or the lower boundary. So I could write you the formula, but it's sort of kind of maybe not very helpful, so I will just leave it out. But there's an explicit way to understand how these posetsets of lower, how these triangulations precisely look like, which I can just write down. So I don't have to really imagine these in any kind of geometric way. It's just pure combinatorics. But nevertheless, this picture is sort of what lies behind it. So, okay. And so, for example, let me explain the lower, so the lower and upper. So that let me say the three Segal conditions. So, three Segal conditions. Okay, what they express, for example, is that I start with the 4 simplex, which somehow looks like this, and then I can express this in terms of some 3-dimensional data, which corresponds to some simplicial subcomplex given by the simplices of a triangulation of the cyclic polytope in one dimension lower. And so, for example, in this case, it'll just look like this. Just I can, up to combinatorial equivalence, I can just think of this as 2 simplices stacked upon one another. So the curve, this moment curve, it kind of approaches like 0, 1, 2, 3, and then 4. That's kind of how it winds around. And so then these 2 conditions correspond to two triangulations of this polytope. In this case, I will actually have 0, 1, 3, 4. Then I have 0, 1, 2, 3, and I have 1, 2, 3, 4. So these are precisely the simplices that kind of touch this diagonal that stretches from 1 to 3. So you see they all have the common edge 1, 3. So and those 3 simplices that wrap around this kind of vertical diagonal. And then in this case, it's just the 2 simplices which I used to glue this guy together. So it's simply, so this would be the lower triangulation, and then the upper triangulation would be 0, 1, 2, 4, and 0, 2, 3, 4. Okay. And so I see, for example, already that I kind of succeeded in my attempt to try to generalize some sorts of Pachner move, because, for example, if I could construct a simplicial object such that these 2 guys here, restrictions onto these subsimplicial sets of the 4 simplex are equivalences, then I would actually end up with a 3-2 Pachner move. So there's, instead of this 2-2 Pachner move, which corresponded to the 2 Segal conditions, here I will actually have a 3-2 Pachner move. But again, it'll come to you as a coherent family of such moves, where all the possible ways of applying these moves are connected by some higher coherences. Okay? Okay, so now let me maybe formulate a bunch of very basic statements, which are basic in the sense that they rely on some hard work, which was done by combinatorialists in this subject of polytope theory. Just basically understanding the lattices of triangulations of these polytopes to a certain extent, certain posets of triangulations. And so, for example, one of the things which I can prove in this context is actually the following statement. So maybe we should first point out that so in relation to what we discussed the last few times, is that we have on the one hand the statement that what we called, or what Resk called, a Segal space in this language will now be called a lower 1 Segal space, because I'm looking at the lower triangulation of this guy here. I could as well look at the upper triangulation, but that's kind of too boring to consider maybe in this dimension. But that's sort of equally justified to use as a descent condition. So we see that lower 1 Segal is actually the same as what we called Segal before. And that's already actually not completely obvious. I have to think a little bit. Actually, if I require lower and upper 2 Segal, right, so that's in each dimension only 2 triangulations, the maximal triangulation and the maximal triangulation. Whereas in our definition of 2 Segal, we actually required for every triangulation of any polytope to be such a condition, but this is actually implied by combining these 2. So this is actually the same thing as 2 Segal. So that's the way it generalizes. So we're kind of taking these 2 conditions of the 2 triangulations apart into 2 different pieces, and then we can also generalize these statements. For example, we proved, therefore, that a lower 1 Segal object is automatically a lower and upper 2 Segal object. That statement, for example, generalizes, and that already uses some sort of interesting combinatorics of this polytope. It generalizes to the following statement. So which is that lower, so in fact lower or upper D Segal, it implies lower and upper D plus 1 Segal. So, which means that again, like in particular 2 Segal spaces provide you with examples of 3 Segal spaces, 4 Segal spaces, and so on. So we already have a supply of interesting examples just for free, just interpreting these lower conditions and for getting some, making them weaker, and looking at these higher dimensional. Okay, so Mikhail and I actually conceived this definition already a long time ago, like maybe, I don't know, like 6 years or so, but we were kind of embarrassed to write it down because we didn't really have any interesting examples. So that's of course the question. Does this condition make sense? So can you construct interesting examples? And so that, well, on the one hand, we sort of had enough to do with 2 Segal spaces. That's why we didn't really try all that hard. But on the other hand, we also didn't really have any systematic idea of how to produce these examples. And so that has recently changed because there's been a lot of energy devoted into this search of whether you can find such examples. And interestingly, so this should be probably taken as a general philosophy. So interestingly, they again arise in algebraic K-theory. You just have to look at sort of a little more unknown corner in algebraic K-theory, which is the following. So let me now give you examples of interesting examples of these higher Segal spaces, which again arise, as it turns out, via a version of the S construction, just a higher dimensional version. So for every D, you can also do this for 0, but let's just say this. So consider the what is called maybe K, the K-dimensional S dot construction. So let's say Waldhausen construction. But it actually doesn't arise in the work of Waldhausen, but it rather arises in its lowest dimensional instance in the work of Hesselholt and Madsen on real algebraic K-theory. So now we see various, essentially all the constructions all the simplicial constructions you write down in algebraic K-theory, like the Hermitian S construction, also these higher dimensional S constructions, have an interpretation in terms of this structured theory. So this is the K-dimensional S construction of, let's say, any abelian category A. Which is defined as a subset of diagrams of the poset of functors from, now we use this K, comma N. Okay, so remember, in the S dot construction, we had basically a 2-dimensional shape where we used the coordinate grid with indices I, comma j for the objects. That corresponded to the fact that we use 1 here. So now we actually have a higher dimensional shape with a k plus 1 dimensional shape, actually. That's the way we should think of it, which uses k plus 1 tuples of elements in N to parameterize this. So look at this, and then look at the subset spanned by diagrams that are of the form, so let's say A fun K N to A, satisfying the following conditions. So in Waldhausen's case, we had various conditions which said that certain of these vertices were supposed to be 0 objects in the category. And then there was a bunch of short exact sequences that were supposed to, also a bunch of sequences that are short exact. So it's exactly of the same nature here. We have number 1, A of any degenerate is equal to 0. So if tau is a degenerate K subsimplest, so it's not an injective map, in other words. So T is degenerate. Second condition, for every non-degenerate, so that means injective map of a k+1 simplex inside N, we get a long exact sequence, which is given by del k+1. Which is given by a del k+1 of the simplex. Right, so there's actually a sequence of this kind, del k of the sigma all the way up to del 0 of sigma, or so rather, right? So this sequence exists just by parameterizing these, just by the definition of these diagrams, and the sequence is supposed to be long exact. So if I also have to include zeros here. Okay, so let me maybe write down an example. So how does this simplicial object look like? Looks precisely like this. So for example, the two-dimensional S construction. So that should be called the Hesselholt-Madsen construction. Because they use this in the presence of a duality on this category to provide a genuine Z-mod 2 equivariant delooping of the K-theory spectrum. That's a really beautiful idea, which they use. And so this object looks like this. It starts with zero simplices. So zero simplices again, zero objects. Then I have the objects of the category again. So I'm just going to write this kind of sloppily. And then it starts to become interesting. So here, right? So the S construction started with objects here, then short exact sequences here. So here I'm just drawing, and let me draw this in a little, in actually a three-dimensional way, as I should. So A 0, 2, 3, A 1, 2, 3. So the reason why I write it like this will become clear in just a second. So here I now have a 0, 2, 2. So this is degenerate, so therefore it's supposed to be a zero object. Then I have a 1, 1, 2, a 1, 1, 3, a 1, 2, 2. And so I should really actually think of this as a cubical shape. That's what this, what the dimensionality of this construction suggests to me. And then I see that the non-degenerate objects actually correspond to precisely these guys here. Sorry. And this is precisely the sequence which is supposed to be exact. What's interesting is that this way of writing it in this three-dimensional shape, it also provides an immediate generalization to stable infinity categories. Here I'm just supposed to draw this cube, and this cube is actually supposed to be, so this is actually the proper way of writing down, for example, a four-term complex of objects in a stable infinity category. I have these two objects, a zero homotopy, right? So each of these are going to be zero. So one zero homotopy, another zero homotopy somewhere here, and then another homotopy which relates these homotopy. That's sort of the third dimension. And so the condition, the correct condition in stable infinity categories to say that this complex is actually exact, meaning that its totalization is zero, is simply saying that this cube here is bicartesian. So this therefore also works. So in stable infinity categories, you're supposed to say that this is a bicartesian cube. Okay, so now here's the theorem. So this is a contribution of Thomas Pogundke, which is really the first sequence of examples of higher Segal spaces in dimension bigger than 2. Is that so S dot? So what I should, I should always somehow take maybe this as a space, but I actually don't. For any dimension, this k-dimensional S construction of an abelian category is a lower plus upper 2k Segal space. Okay, so that provides us. Say it again.
A is a abelian category or stable?
The A is, so in his result, A is an abelian category, but it also generalizes to stable infinity categories, which is kind of the context relevant for the remaining discussion. So the proof for stable infinity categories is actually easier than the proof for abelian categories, I think. So yeah. Probably a typical phenomenon. So abelian categories are harder than stable infinity categories. Okay, and so I'm supposed to stop earlier, so let me just, so this is now kind of nice, like, because so these examples, like the general versions of these, the higher dimensional versions of these S constructions, they satisfy these Segal conditions precisely in even dimensions, and in even dimensions, of course, also exactly where you try to construct something that comes from symplectic geometry. And so this is sort of one long-term thing in progress, to use these ideas to actually really define higher dimensional TFTs of some sort that capture certain degenerate versions of these Fukaya categories from symplectic topology. But let me maybe just finally state a result which was inspired by this whole context, which I find has sort of is maybe of independent interest. And that's the observation that if you look at all these S constructions in the various dimensions, for example, if you look at, so this is a simplicial, let's consider this as a simplicial exact category, let's say, and let's pass to the Grothendieck group level-wise. Then you actually get a simplicial abelian group, and that simplicial abelian group is precisely an Eilenberg-MacLane space of dimension k based on the group k0 of this category A. So in other words, you should think of as Waldhausen's S construction as a categorification of a k pi 1, and these higher dimensional ones as categorifications of k pi n, and sort of the way they arise is actually in a specific model to construct these Eilenberg-MacLane spaces via the Dold-Kahn correspondence. I just take a complex which is concentrated in 1 degree, and I apply the Dold-Kahn nerve. That gives me a simplicial abelian group, and that's precisely a model for this kind of a Eilenberg-MacLane space. And now, motivated by this and various other constructions, I'm thinking about also in joint work with Mikhail Kapranov. You actually notice that you can actually categorify the whole Dold-Kahn correspondence so that these objects here arise as precisely Dold-Kahn nerves of complexes of stable infinity categories concentrated in 1 degree. And so this is the following theorem, which I think is somehow a precursor of some general theory of two-categorical homological algebra with coefficients in stable infinity categories. So I'll use this to conclude. Of infinity categories, where on the one hand there's a certain kind of simplicial stable infinity categories which are parameterized by the 2 simplex category, and then on this side here there are connective chain complexes of stable infinity categories, so there's functors in both directions. It's an equivalence of infinity categories, and so here it's maybe interesting to point out is that this guy here is the 2 simplex category. So this kind of an approach actually arose in discussions with Thomas Nicolais, I should say. So the 2 simplex category. Usually the simplex category is defined as a full subcategory of the 1 category of categories, but you could as well define it as a full 2 subcategory of the 2 category of categories. So the simplex, 2 category. And then, I wanted to call this a 2 simplicial object. So should I call it a simplicial 2 of, I don't know. So so these are 2 simplicial objects. So right, so ST is the infinity 2 category of stable infinity categories. So this is basically the definition of this side here. It's just cut infinity enriched functors from this guy here into this guy here. So you have to think about a little bit how to find a proper model for this, but it's just a kind of obvious strict one, and then you localize. And on this side, it's just really the naive notion of a complex of stable infinity categories. So it's just a sequence such that the composite of two functors is a zero object in the functor category. So in this world of categorified homological algebra, there is nothing like Massey products for this reason. So it doesn't make sense, so it's kind of uninteresting to talk about coherently trivialized complexes. And so yes, I was sort of intimidated by trying to prove this result for a long time, but then once you actually start thinking about how to do it, it can be done by really a step-by-step categorification of all the techniques you use in one version, at least, of the proof of the ordinary Dolcan correspondence. It's just slightly surprising because stable infinity categories, for example, are not additive in any sense. I can take a sum of two functors, but I cannot take a difference. So I could somehow force this to happen by passing to some non-commutative motives. Then I would, for example, recover a version of the Dolcan correspondence by Jacob Lurie. But this is not what this is. It's really on this unstable level. And so the technique you use is actually that from this two categorical data, whenever you have to take a difference of two objects, let's say, then there will be a map relating them, and you just take the cofiber. So cofibers generalize the possibility of taking differences. And then the usual splittings, which you see on a simplicial abelian group, for example, that arise in the Dolcan correspondence, they correspond to more complicated gadgets, which are semi-orthogonal decompositions, but those can also be explicitly controlled by writing down gluing functors that glue these decompositions together. So I think this is probably a result of independent interest. Also suggests the existence of some version of homological algebra, which I can do in this context. And one result, which is joint work in progress with Gustavo Haas, so let me conclude with this, is that actually, more generally, you can construct examples of these two K-Segal spaces by just starting with any chain complex here, which is concentrated in degrees 0 to K, and applying this nerf. So it's like a kind of large generalization of Waldhausen's relative S construction, which would arise from a two-term complex. The usual S constructions arise from shifting this object in the various degrees, so that's these higher dimensional S constructions. But the statement that you get something 2K Segal, it simply has to do with the fact that you look at something truncated here. And the way we prove this is also interesting, is that these guys, they sort of behave somewhat like Kahn complexes. So they satisfy certain horn filling conditions, but you have to interpret these horn filling conditions in a two-categorical sense. So for example, let me give you one example. If you look at such a horn in the 2 simplex, you would also have to remember a natural transformation which points from this edge to this edge. And then, given this additional data, you can actually fill this horn. So this is the kind of stuff you do. So I think it's just an interesting starting point to play some further games in this categorified version of homological algebra. And so I think I'd like to conclude here. Thank you.
We have time for one question for Toby. I'm free to ask it, am I?
No. So in the simplex 2 category, there's a whole bunch of adjunctions.
Yes, right.
So what does that correspond to in the right-hand side?
There's nothing. I mean, so here it's really just a naive notion, like you have, so I mean, these adjunctions, what they realize is just sort of, they correspond to data which makes the usual direct sum decompositions, which you see in a simplicial abelian object, into some glued version of it, where somehow the two components of the direct sum are actually glued together in a twisted way. So that's what all these adjunctions somehow realize. So, and that's also how you prove it. Actually, you peel off these semi-orthogonal components just layer by layer, just as you split off the summons in one proof of the Dolcan correspondence layer by some inductive argument. So. Yeah, so the fact that all these, for example, one of the implications of these of the two categorical data is that all these functors that relate cells in 2 different dimensions, the phase degeneracy, and so that these are actually adjoints to one another. So that already sort of explains that there's a certain redundance in this object, which maybe makes it less surprising that it's recovered by less data. So.
Well, let's thank Toby again for a brilliant talk.